Okay, let me see something before we get started. Much to my somewhat surprise, they're going to try to run 4130 next semester. So even if you didn't sign up, and especially if you did, if you're interested in taking Algebra 2, that will be offered, assuming it runs next spring. And it will take the place of, so now what they're doing, they're signing off for this, and I think they're going to make it a rule. See, but right now you all have to take a semester of algebra and then 2 of advanced calculus, right? You can substitute out 2 semesters of algebra and 1 for advanced calculus. So you can do that change if that's something that you want. If you're a math concentration, you should probably do both also. So anyway, so the last time we were talking about rings, and this is the last thing I left you with. If R is a ring, then 0 times anything in either order is 0. This is what you would hope it would be. Negative A times B is A times negative B. Now remember, the negative A is the additive inverse method. That's what that is. And that's negative AB for all AB and R. When you multiply negative A times negative B, you get AB for all AB and R. If R has an identity and the identity is unique, and negative A is negative the identity times A for all A and R. And the last one, M and N are integers, RS and R, then MR times NS is MN times RS. What do I mean then? What does MR mean, right, when R is ring? Well, here, M times if M is greater than 0, right? So 1 R is just R itself, 2 R is R plus R. And absolute value of M times if negative, and of course 0 times R is 0 at both part A. Right. Let's look at a couple of these just for fun. Yes.
So, cause like rings have like the addition and multiplication. We also see that it, or no, never mind.
Okay.
Never mind.
Okay, so let's look at a couple of these here. So let's get you proof of some of these. For example, if we look at 1, if you look at 0 times A, it's some element of the ring. This should be 0. Right? Because I don't know what 0 times A is at this point, but it's some element of the ring. And when I subtract that, the additive identity is 0. Now, because this is a ring, I've got that, right? Distributive property, I can pull that out. And 0 minus 0 is 0. And there we go. That's the only one I'll prove, but just put the A on the other side and go through the same computation, and you'll get this as well. Any questions on that? 2, I'll get you warmed up on this one too. If we look at if you look at negative AB times AB, look at it. This is equal to negative A plus A times B, because we have the distributive property. So I can pull that B out. Right? And what's negative A plus A? 0. And we already know from the previous part that when I multiply 0 by anything, it's 0. So there we go. So negative A times B negative A. Just adding negative A B both sides because it's an adding. And put it, it's similar to do the other part there. Okay. Let's sketch 3. Negative A times negative B, negative A. So, if you look at negative A times negative B, this is A.
Me, just a time. We have to cover some of these. I did homework.
Previous right here allows you to switch the signs, right? I can take the negative in front of first A and put it to the next, right? And negative B is just B.
I'm gonna see write things down because I kind of wrote it like it's the rain, you know.
Number 4. If R has the identity, then it's unique. Well, let's now this is very much what we did. If you remember back in the day, we had a theorem or result group that said if there's an identity, which you're assuming in a group, that identity has to be unique, and the proof is almost the same. So suppose I've got 2 identities, I and J. So when I'm multiplying anything in R by I on each side, it leaves it alone when I multiply by J on each side. So I equals I J because J is an identity, but I is an identity. So this is equal to J, right? I mean, it's almost, I feel like he used car sales or something, but that works. Also, let me start off by observing that minus A plus A is, of course, 0. Oh, sorry. What is this? Well, notice I can pull an A out. I can pull A out of the, actually, I can pull A out of either side because A can use the identity. So it's a little sloppy there, but same by factor. The identity uses everything. And since the identity is unique, these two are the same, this is 0. So in particular, so if I take this over to the side, minus 1R times A, which is what we promised. Okay. We show 5. So I'm gonna show just 5 for M and N being natural numbers as opposed to integers. We will proceed by induction on M. If M equals 1, then what do we have here? We have R times NS, which is just R multiplied so let me write what this means. What does NS mean? Well, N is the natural number. So this is just an S added to itself a bunch of times. N times. Right? Well, we've got the distributive property. So you can suck R into this. And it distributes throughout. So this is equal to RS. 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 Also exactly N times. Right. Exactly as many RS's as there were S's previous. And this is N RS. Equals RS. So this works for M equals 1. Now we will assume this holds for M. That is M R N S equals M N R S. And we build a ladder. Let's check out what happens M plus 1. Oops, M1. R. Well, so this is now this is equal to MR N S plus R times NS. Correct. Because we have to distribute MR times NS. Now, by induction, we know what this is. By induction, this is M R X. And by the base case, this is N R S. So you've got M N R S's and another N R S's. So this is M N plus N R S's. And I can pull an N out of that.
Okay.
And that is static. Now you might say, what happens, Jim, you big fat cheater, you only did this for the natural numbers. This is not a problem because you can use these previous parts to take care of what happens if one of those is a negative or if they're both negative or 0. Okay, any questions?
Sorry for being late. It's the rain, you know. Those are all the on that homework, you know. Maybe better on homework 9 then, you know.
You're pretty.
Sorry, it's always passing now.
Okay, definition. 9-1. I'm gonna find something that's kind of interesting. These are particular types of elements in a ring that might be of, interest.
Yeah, I think they're covering on that one. I already did work on that one.
Number one. We say that we say that A is a left. Respectively right. 0 positive. If there exists, and this is important, a non-zero BNR such that AB equals 0, or respectively, BA. Let me read this for you. Well, respectively means you can read that second. So you say that A is a left zero divisor. If there's a non-zero B, since that A times B, so when you hit B on the left of A, you get 0. B has to be non-zero. We say it's a right zero divisor. If there's a non-zero B system, when you hit it on the right, you get 0. Right? It does not have to be the same B. Yes.
So whenever you have like, whatever makes a left zero divisor also makes its corresponding B like a right zero divisor.
Oh, I see what you're saying. No, not necessarily, because 0, by my definition, if you have a ring with identity or have a non-zero element ring, then 0 is a zero divisor. Because, for example, let's suppose you have a ring with identity. 0 is a left zero divisor because 1 is not 0 and 0 can form a 0. Right.
So
So
it brings up and then just the concept.
only the criminally insane work with rings without identity. Although we might build it without that. Yeah, it's actually rings without identity have lots of problems, believe it or not. Thing, but we will look at some of those. We say A is a zero divisor. If it is left and right. Zero. By the way, it does not have to be the same B. For example, you might have a non-zero B since the AB is 0, and a non-zero C since the CA is 0, and that's 0 5. Here is a zero divisor on steroids.
Oh, nilpotents?
Right.
Yeah, I did that homework, I mean, it's.
No. Notice that any nilpotent is zero divisor, right? Because, for example, A squared is 0, A is both left and right, zero divisor, right? I count also 0 to be a nilpotent element as well, right? And finally, sort of the antithesis of all this, if R is a ring with identity, we say
Units
U and R
is a unit.
unit. If there exists B and R such that B this side. So a unit just means it's a vertical. Loosely speaking, what it means is it's an element whose reciprocal is still in the name.
Yeah,
I was just wondering about e to the ends, that is repeated multiplication.
Yeah, that's right. It's just that it's just repeated multiplication. Now, whether something's a unit or not can depend on the ring, of course. What are the units and the integers? Only 1 and -1, right? 2 is not a unit, the integer, because 1/2, not an integer, right? However, in the rational numbers, 2 is a unit, because 1/2 is in fact a rational number. If I give the distinction. So let's look at some examples here. Can anybody give me an example of a ring that has a non-zero zero divisor? Uh,
And,
into,
oh,
give me a non-zero zero divisor.
zero zero divisor.
Remember, this is.
Right, I should make it since I know. I understand. Well,
Anybody wanna guess
Well,
what?
I think probably a nilpotent element is a zero divisor.
That is true.
So I actually know a nilpotent element in there. So it's gonna be a 1 and 0 0 0.
Like that?
Well, I'll probably guess place 1 like in the 0, so switch the 1 and the 0, and that'll be the 0 divisor. Yeah, that's the one. I think now over at ChatGPT, like find an example for me, you know? Something over. That's why you use ChatGPT for your homework, because it's easy to give examples for you, you know? Once you know what the specific rule set is. It also brute force.
It's pretty easy to show that we sort of think it should go. How about, okay, so he gave me a nilpotent. Anybody give me a zero divisor that's not nilpotent?
Probably 1 0 0 0.
This is an example of zero divisor that's not nilpotent. How do I know it's not nilpotent?
Because the times itself is just 1 0 0 0. So
This is what it's called idempotent. Because it's an element idempotent. It's an element that squares to itself. Now, in the real numbers, the only idempotent real numbers that I can think of are 0 and 1, right? Do I agree with that? Those are the only items, but there are plenty of idempotent matrices. Right?
it's multiplied.
And this has to be a zero divisor, right? Because in fact, you could use this equation that we've got here to figure out what you can multiply to get it 0. So in this ring, and this is a ring, matrices form a ring. So somebody give me an interpretation of B minus one.
Okay, so it's going, 0, 0, and then on the bottom row is 0, -1.
B, this original matrix here. Now subtract the identity, which in this case, is 2 by 2 identity. And you 0, 0, 0, -1. If you multiply B and that matrix here, they're both non-zero, you get the 0. Okay, so this is a big ring that's got, matrices are, by the way, can somebody tell me how we can figure out what the, what are the zero divisors? Can somebody tell me how to figure out what the zero divisors are here? Characterize? Okay. Okay, how do you use it? Well, let's justify that though. How do I know that? If you think back to linear algebra, what does it mean to have determinant equal to 0? It means it's a singular matrix, right? That means that if in square matrix, that means that there have to be vectors that go to 0, right? Non-zero vectors go to 0. So the kernel of this linear transformation, Barfield in the path has to have a non-trivial kernel. See if you can use that to show that this thing always has 0 divisor. What's true about matrices whose determinant is not? You know, they're, well, that's right, but structurally, from the context of what we're talking about, they're always what? What do you know about if you have a matrix that has a non-zero determinant, what's the first thing that jumps out at your mind? What's true about that matrix? It's invertible, right? Everybody remember that? And if it's invertible, it's a unit. So we find that in this ring here, one of two things is going to happen. Determinant is 0, it's a 0 divisor. Determinant is not 0, it's a unit. So it looks to me like everything in this ring is either a unit or a 0 divisor. Can anybody give an example of a ring that has an element that is neither a 0 divisor nor is it a unit? Okay, but most of the integers. You can see 0 is the only 0 divisor. Plus and minus 1 are the only units. Everything else is what is often called regular element, neither a 0 divisor nor a unit, right? If you look at 2, it's not invertible, it's not a unit, and it's not a 0 divisor. So it doesn't do anything weird, multiply itself to 0. How about another example? How about this one?
Okay.
How about Z12? Can anybody pick out units? See, you're letting me pick the low hanging fruit here. Certainly one is always a unit. What's it now?
6 squared.
So can you multiply 6 bar by anything and get 1 bar?
One.
That's right, because to be a unit, you have to, so to be a unit, you've got to find something else that multiplies them together to get 2. Here's the problem with 6 bar. It's got a factor of 6 in it. Right? To get to 1 bar, you've got to shake off that factor of 6.
I was trying to send it to 0.
Okay. How about the units?
11.
That's right. And that's a, you can think of this as a clever ripoff because 11 is essentially -1, isn't it? Right? Are there others? 2 others. Is it?
5 and 7.
What do those 4 numbers have in common? That is correct. These are the only numbers between 0 and 11 that have no factors in common with 12. Agreed?
Well, 1.
What about 1?
Is it 1 in factor 12?
What's in it? Oh, non-trivial factors.
Okay.
Thank you. Right. So let me rephrase. This will make it sense. These are the only 4 numbers between 0 and 11 whose GCD with 12 is 1. That's right. Notice that these are all their own inverses too. 11 times 11, 1, right? 5 times 5, which is 25, it's 1 minus 12. 7 times 7 is 41. So these are their own inverses, right? And that's it, right? This is why the Euler phi, do y'all remember the Euler phi function from way back when in class, where it counts the number, Euler phi of x, or of n equals number of x such that counts the number of numbers between 0 and n that are relatively prime to n. This is exactly that number. It tells you how many units are in this. Okay, how about 0 divisors? See, that took faith in my book. That's right. You got the low hanging fruit. What else? 6 is true. In fact, I'll go a step further. Everything not already listed is a 0 part. But 2, 3, 4, 6, 8, 9. Why are these things 0 divisors? Well, notice, for example, 4 has 2 factors of 2, right? Now to make the 0 mod 12, all I got to do is hit it with 3, which is not 0. 4 times 3, 12. 2 times 6, 12. 8 times 3, 24, which is 0. 9 times, what do I mean? 4, 36. Everybody see the pattern? So in this ring again, everything is either a unit or a 0 divisor. So this is like they're a matrix example. How about nilpotents, if any? well, there's always one, zero. Zero's nilpotent. Are there any others? You need a power of something to have multiple 12 in it. So for the power to have a multiple 12, that thing has to have every distinct prime factor of 12, namely 2. Right? So let me point out that if you look at the ring Z6, it will have 2 units, 1 and 5. Everything else is 0 divisor, but only 0 is a nilpotent. All right. See if you can figure out what the pattern is.
It's, don't. Like you. Like it's 25.
Oh, sure. Yeah, U and V don't have to be different. That's right. Let me give you the following proposition. Which I think you'll find it's not too difficult.
I was wondering, so if it's just that it has to be a to some natural number, because there, then couldn't you just say for like one, for instance, say like 1, 2, or, well, oh, I guess you're multiplying. Okay.
Well, R be a ring with identity. Then U R. Set of U and R, such that U as a unit. Is a group. Under. Multiple. Let suppose you have 2 elements U and V that are units in R. So there exists X, Y, and R such that now, look at so they you look at UV comes YX. This is U,
It's associative.
this is Y, and which is UX, because that's the identity, which is R. And if you look at YX times UV, this is Y times XU C, which is YV. So you are close. Right, 2 units is still a unit. Multiplication is associative. And this is because R in ring. Because we already know coming out of the gate, the R is a ring, so multiplication is associative. Don't worry about that. 1R is identity for units. 1R is of course a unit because its inverse is itself. And it is the identity of the ring, so functions the identity here. And for all U in U R, there exists X in R such that U X equals X U one R. With inverses. And note, X is in UR by definition as well. No surprises there. Okay. Any questions? The next one is a homework problem, but I'm gonna record it. This might be convenient for your notes. 8. Here we're going to assume that R is commutative. Put R be and X, Y, R, nilpotent. Then X plus Y and X, Y are nilpotent. You prove this in your homework. This is actually pretty easy to prove the product is nilpotent.
Yeah, it is a bit difficult, but you remember like the rules about like multiplication,
But
it's
it's
like,
not too bad.
yeah, it's not that bad, you just gotta learn foils, if I learned like seventh grade. You learn stuff like this, like basically like the multiplication two like polynomials together in like seventh grade. You're gonna apply it here as well.
In addition, R has an identity. And U is a unit of R. Then U plus X is a given. So the second statement requires commutativity, but it also requires an identity. If you have a unit and plus a nilpotent, then what you get is a unit. If the link's commutative, you can sniff around and find in Will's problem set that these statements are wildly untrue if you remove the commutative from the equation there. Definition. So we kind of flirted around with this a little bit. What are a ring identity? If R minus 0 is a group under multiplication, we say R is a division. So if every non-zero element, so basically what you're saying is every non-zero element of this ring is invertible. That's what you're saying when you're saying that when you pull out the zero, it's a group under multiplication. It means every non-zero element has an inverse in that ring. We call such a ring a division ring because you can divide any element by another element as long as what you're dividing into it isn't zero. Yes.
So is everything a unit then? Take 0?
Except for 0, that's right. A commutative division ring is called anybody know what it's called? you have division rings commutative, so every non-zero element is field. And this is the terminology that you hear in linear algebra. How many of you have heard, at least in passing, the terminology field when you were in 3110? Of course, probably in 3110, you focus mostly on the reals, which is a great example of a field. Every non-zero real's reciprocal is also a non-zero real. The fields are where you can do linear algebra, and there's lots of them. If you look at Z mod 2, that's a field, right? Because the only non-zero element in Z mod 2 is 1, which is important, right? Q, R, C, this means rational functions. So you might have seen this as well. This is rational functions, this quotient of two polynomials, coefficients Q, these are all fields. C mod P for P prime. These are all fields. Can anybody give an example? This is a little trickier. Anybody give an example of a division ring is not a field? That is a division ring where the multiple. How many of you, okay, I'm fixing to get some bright eyes from physics people out there. How many of you have heard of the fraternities? Right, heard of those? Right. On a division. Now, and Henry, I want to help you out with that. So, yeah, isn't this something we saw in groups? It's today, and it is. So you all know complex numbers, right? And I squared make it 1. Right? So this is an old friend complex, right? The quaternions are more ambitious. In fact, you ought to play around with this, see if you can sort this out. And they're related to that group Q8 we saw, because what this is a set of A plus BI plus CJ plus DK, where I squared, well, A, B, C, D, in reals, and I squared, B squared, N squared, -1, IJ is K, JK, I, K, I, J. The quaternion relations that we had earlier, you all remember that. This actually forms a division ring, but it's not, right, so it's not. I'm going to leave you with one last definition. Definition. But are the musical it is important. This is a very important central part of the definition. It has to have a 1 in it. R is an equal domain. And sometimes I abbreviate, just call it domain, but it's an integral domain. If 0 is the only zero value. So there are no non-zero zero values. This is why you are going to love integral domains. Because what happens in integral domains is the crap you've been doing forever in your life, that's where it's true. If A and B are in R, then A, B equals 0, because A equals 0 or B equals 0. You've used this in a lot of earlier high school math classes and stuff. You're solving equations. Oh, I factor it. So one of those polynomials has to have a root. This is exactly use the fact that it's an integral domain. And these are the rings where you can play that kind of game. Okay, we'll talk more about this next time. Any questions? Yes.
Integral like integers, not integral like outputs, right?
Yeah, that's right.
Okay, sorry.
Yeah, I haven't gone.